Let's pick up where we left off. We went through sampling. Today I'm going to go over several important issues when it comes to sampling. One is the issue of aliasing in a frequency domain. Give you some practical consequences of the sampling theorem. Namely, I'm going to talk about sampling in quantization, which is the basis of the PCM, pulse coding modulation that we use extensively in telecommunications, and talk about TDMA, which is one of the most important schemes for sharing common communication resource. And then towards the end, I'm going to start talking about something that's a prelude into discrete Fourier transform. We've been talking so far about the Fourier transform, and there are a whole bunch of integrals, right? The problem with integrals is they are not really, or they're not directly computable by discrete processing machines like our computers. So we have to have a way of doing this in discrete domain. And this is what we do when we're doing discrete Fourier transform. Okay, so let's first talk about anti-aliasing filter. Okay, so one of the prerequisites of sampling theorem, for the sampling theorem to work, the signal needs to be band limited. Now, a lot of signals are band limited, but after very large frequencies. What typically you observe is that the signal has a bulk of a spectrum within a certain range, and then the power spectral density of the signal kind of tapers off towards infinity and becomes smaller and smaller. But many signals have components that extend far along the frequency axis, even though they carry very little power. So what we typically do in pretty much all the systems that process the signals using sampling theorem is we actually cut off at some point. And where the cutoff point is, that depends on the particular application. We know how to do this based on our Parseval's theorem or the energy of the signal. We know that we can determine the bandwidth just from the requirements to preserve certain amount of energy or certain amount of power. So we, based on experimentation or whatever may be the case, determine what the bandwidth is. And before we sample the signal, we process the signal with a filter that cuts off the frequencies that are above a certain band. This filter we call anti-aliasing filter, the filter that gets rid of high frequency components. So here's how sampling theorem works in practice. You have your signal x of t, then you have your filter that gets rid of a f filter that gets rid of the high frequency components. You have this x filtered of t, and now you sample this by multiplying this by some sort of sampling sequence. In this case, I'm using the delta pulses, but we've seen in our previous considerations that this can be any periodic sequence that we can use for sampling. So this is n goes from minus infinity to plus infinity, extension xf of nt times delta of t minus nt. So this is our sample signal here. So let me draw a couple of pictures that illustrates what the purpose of this filter is, although we kind of know it, but let's just, I'm going to use this section of the board here. So without a F filter, this is what happens. Your signal has, a spectrum that might look somewhat like this, where there's a bulk of the signal power that is in this area, or signal energy that is in this area, and then it kind of tapers off as a function of frequency, so this is magnitude x of f. If we sample this signal, what happens is, as a result of sampling, the signal is extended periodically in a frequency domain. So let's say this is your sampling frequency. As a result, you end up having something like this, right? And what happens in this range here, you have a mixture of the frequencies that are coming from the baseband version of the signal and its periodic extension. Therefore, your reconstruction becomes impossible here. You have a mixture of this signal and this signal. And remember how we do reconstruction process. We essentially filter out this baseband version of the signal, which is the same as the convolution with the sink in the time domain. But if I try to do this in this case, then see what happens. You have part of this signal leaking into the spectrum of the original signal. This is what we call aliasing. Now, with this filter here, this is what happens in the frequency domain. We filter our signal, so this would be X filtered of F. And now this was original spectrum of the signal, but now the filter cut off the high frequency components. So essentially, you have a signal that looks like this. Right, and I'm kind of exaggerating here so that you can see the drawings, right? So I got rid of all the high frequency components, and my signal now occupies just from here to here, right? And this is what we call bandwidth. The bandwidth is now defined by us and within our control, because we got rid of all the components that are outside. This makes sampling quite easy because now I know that if my Fs is larger than this well-defined bandwidth B, there will be no overlap in the spectral domain. So now I have my signal looking like this. And then its periodic extension will pick up from here, and then on the other end, and there will be no overlap. So I guess here, no overlap. So this is XF, F minus NFS. And this is X of F minus NFS. Magnitude in all cases. Okay? So that's what we always do. As a result of this process, however, the signal is distorted, right? Because we're getting rid of some of the signal components, and as a result, the signal is not the same as it was, right? But that's the bad news. The good news, it's completely within our control. We are the ones controlling how large the B is, and depending on a particular application, we can make it larger or smaller. If it really bothers us and whatever is distorted as a result of this low-pass filtering is significant, then it's within our power usually to change this and make it larger, and then therefore get a signal that is closer to the original signal. Let me give you an example of this process so that you can see the trade-offs. So, put here, example. And the best example is probably the simplest one too, is your telephone voice. Now, the voice signal has frequency components up to 15 kilohertz. It's actually, it may have even beyond it, but we don't hear it. So, what I say, produces some energy all the way up to 15 kilohertz. But when you look at the energy of what is being produced as a result of somebody talking, it is not distributed uniformly. Bulk of it, or actually 99% of it, is between 300 hertz and 3.4 kilohertz. So most of the energy is in the frequency range between 300 hertz and 3.4 kilohertz. Right? I forgot exactly the percentage, but I think 99% of energy is within the range from 300 hertz to 3.4 kilohertz. That's where our speech is. This is also where our ears are the most sensitive, and that's not by accident. Right? Our ears are the most sensitive around 1 kilohertz, and that's where the majority of what we produce as speech is actually centered. So this says, okay, if I limit my voice signal to 3.4 kilohertz, then I can sample it comfortably. I can declare that my bandwidth is 4 kilohertz, and I can sample it comfortably with 8 kilohertz, 8 kilosamples per second, and have a nice separation in the frequency domain and ability to reconstruct this easily. So the voice signal is therefore filtered. So the signal is filtered with low pass, with cutoff frequency of 3.4 kilohertz, and the sampling frequency, which we know has to be greater or equal than 2 times the cutoff frequency, is selected as 8 kilohertz. Right, so there's about 600 kilohertz between fs over 2 and the cutoff frequencies to allow to a relatively smooth roll-off of a low-pass filter that is used for reconstruction, right? Because you don't want to have the brick filter then, because you cannot implement that. So that's how it's done in the voice. Now, as I mentioned that before, you know that the result of this is that the voice is somewhat distorted, and your telephone voice doesn't sound like your in-person voice. You have to, whenever you hear somebody over the telephone, you have to learn how do they sound over the telephone, because it's different. But after you go past that, we've preserved most of the signal energy, so there you most of the time you have no problem understanding person speaking. The problems that we have is when there is something that that is out of the context, right? Remember, understanding of a speech signal has to do with 2 things. One is hearing the words, and then the other one is hearing the context, right? Because the sentences carry its own redundancy. You don't speak random gibberish words. You speak sentences, and then even if you miss something, you can interpolate and understand the whole sentence. But that all fails apart, for example, when they ask me, what's your first name? Then I have to spell it, right? And because it's a weird name, right? And not only that, I cannot say IVICA, right? Because then that C or V is not easily understood. The reason for people not being able to understand consonants over the telephone is because majority of the energy that is attributed by these consonants is in these high frequency components that we cut out, right? So you have to provide the context. Then you say V like a Victor, right? So they know that it's a V and not B or T or P or any of these, because the part that actually makes the difference between V and B is actually in this part of the spectrum that we cut out. So that's why we say V as a Victor, C like a car, or whatever, so they give them, again, the context so that they understand what the particular letter is. But that's a minor annoyance in respect to the benefits that we get. The benefits now is that, the voice signal is very narrow. It's only 4 kilohertz. So if I look at, let's say, 1.5 megahertz line, T line, then I can fit 24 voice signals over the same line. And this makes the cost of the whole thing go down. Right? So these are the trade-offs that we made all the time, and it's really part of our design and the consensus of what we decide is appropriate in a given application. So let me further with some other application of this. I want to talk about just a little bit about pulse-coded modulation. So some applications. All sampling theorem. One of them is pulse-coded modulation. This is PCM. And this is the way how all of our landline telephony works. Now when I say, I usually say landline telephony, and people always kind of, okay, that's you know, by the time, that's not important anymore because we don't use landline anymore. I don't know if you guys even have landline, right? And who uses landline anymore. But even if the telephony is not used, this is not used in telephony, or telephony is not used anymore, landline telephony, all of our optical fibers, the ones that run on internet, actually implement PCM. So, you know, all this wireless stuff that we talk about is nice, but the backbone of all our communication is on optical fibers that use PCM as the way how the data is being sent, and use TDMA as a fundamental way how the resources are shared. So PCM, TDMA is still running all majority of our landline backbone communication. It is only within the last, what they call last mile access, or from the access point to the user, that we have a lot of wireless access schemes these days. But when you go to as soon as you get into the backbone of our communication systems, it is using PCM, TDMA scheme. So what is pulse coded modulation? Well, here's our story, right? We start with our signal, can be voice, data, whatever, but at this point we assume it's an analog signal of some sort, and we do our sampling, right? And sampling process, as you remember, can be seen as a multiplication between my analog signal and my delta sequence. So my sampled signal at cat of t is given as sum when n goes from minus infinity to plus infinity, x of nt delta of t minus nt. So that's my sample signal. Now, in generally speaking, these x of nt are continuous values. They can be anything, right? Any real number within a certain intervals, from some minimum value to some maximum value. You know, that's in a practical systems that every number needs to be represented. And all of our systems use finite number of digits to represent a given number, right? So that means we can never accommodate continuous range. We only accommodate discrete range. So what that means is this x of nt here is always quantized, meaning it is never a real number as it is sampled here, but one of capital N possible values, right? And so let's let me put this here. X of nt is continuous, but in practice, x of nt is always quantized to one of, let's say, n possible levels. N possible. So what we end up doing is we're saying x of nt is going to be some x cubed of nt, which is the quantized value, plus e of nt, eq, where this eq is the quantization error, right? Here's the wisdom of it. Let me just, it's not complicated at all. This is your signal. Let's say this is maximum value, and this is a minimum value of your signal. Instead of accommodating, how many points are in between these two? Infinitely many. So in calculus, you know, this is having infinitely many points. And in order to represent this function, I have infinitely many values. So if this is, let's say, just for the sake of making it interesting, if the value of this sample is pi, I have infinitely many digits, and I cannot represent this in any computer that I have. So the way around it is, what we do in practice is we take this interval and divide that into certain number of subintervals, and then we declare a single point inside each one of these intervals, and these are my discrete values. How many of discrete values I have? It's again design parameter. This is something in my control. But whatever falls within a given interval is approximated with the center point of that interval, right? And in the process, we make an error in a representation which we call quantization error. And the size of this error is within our control. The more intervals we have, smaller the error is. Go ahead.
Yes, Professor, how do you not determine each of the intervals if you don't know how it's an infinity to infinity?
Well, here's the story. I have the minimum and maximum value. And I say, okay, how large should this error be? Right? How large of an error I can tolerate? And let's say you want to say, okay, I want to make sure that my signal to quantization noise ratio is better than 40 dBs. Then, based on some math that I'm going to cover in digital communication, it tells you, okay, in order to do this, then you have to have 128 or 256 or 512 or whatever may be the number of discrete levels across this interval. And if I decide that I need 256 ranges, then that means that every simple sample here I can represent with an 8-digit binary number. Right? So that's how the story goes. I go with a required signal to noise ratio, and that gives me the number of levels that I need to have. And then the number of levels, I'm going to number them from 0 to whatever is the number, and that gives me the total number of bits that I need to represent each particular sample. So to continue with my voice analogy, so we stop here, and voice example, we stop here, and we said our sampling frequency is 8 kilosamples per second. So I'm going to sample the voice 8,000 times every second. But every time I sample, I'm going to get a continuous number that I now need to represent with something that is digital, right? And what we do in the case of the voice signal, we take this interval from minimum and maximum and divide that into 256 different levels. So that means that every sample of voice that I collect, I'm going to round off to one of 256 levels, and I'm going to need 8 bits to represent 256 levels. So that means in voice, I'm sampling at 8 kilobits per second, 8 kilohertz, so 8 kilosamples per second. Every sample is worth 8 bits. So what is my net bit rate in voice?
64.
It's 64 kilobits per second. Right? So this is called the North American hierarchy. It's the same in European. Let me just actually give you the numbers.
Excuse me, Professor. Another again. And each of the samples, does it have like different coded modulation for each sample, or it has same?
Okay, let me defer that. Let's go through this, and then we'll talk about coding and modulation. Right? So I'm going to consider now what is referred to as North American T1 hierarchy. So North American T1, and T1 should be familiar to you guys. I mean, very often you say, I want a T1 line, and that means certain bandwidth delivered to a particular point. So in North America, this is how our landline telephony is laid out in the United States. We assume that the bandwidth of the voice is 4 kilohertz. We have sampling frequency of 8 kilohertz, and we use 8 bits per sample. So number of quantization levels and Q is 256. Therefore, number of bits per sample n is equal to 8. So your total bit rate, okay, your bit rate is always going to be fs times n, which in this case is 8 kilosamples per second times 8 bits per sample, which gives you 64 kilobits per second. And that's the data stream required to represent the voice. So pictorially, here's what happens. Here's the time domain. This is my voice signal. I sample it this time. And this I get, let me just look at 2 consecutive samples. This, let's say x of nt here is equal to 10.246, right? So, and let's say I have even more digits than that. But I'm going to round that to x cubed of nt, let's say 10. So I'm in the 10th interval, so this 246 I get rid of. And I'm going to represent this x cubed binary of nt. I'm going to represent this as 0, 0, 0, 0, 1, 0, 1, 0. So these are my 8 bits that represent this particular sample. You notice that in doing so, I have irreversibly, this is 10, right? Doesn't look like. I have irreversibly erased this 246. So there is some loss of signal to noise ratio, but it's entirely in my control. You know, it turns out if I do it this way, I'm maintaining signal to noise ratio better than 40 dB, which is actually sufficient for high quality voice reproduction. Now, if I go to the next sample, let's say this is x of n plus 1 t. Now, let's say this is 9.18. Now, going down and falling into the next interval, then I quantize this as x cubed of n plus 1 t as 9, and I represent x cubed binary of n plus 1 t as now 0, 0, 0, 0, 1, 0, 0, 1, right? And then when I try to send this over the line, these are the bits that go first, and then these bits go second, and so on and so forth. Now, going back to your question, right? Now, this is all happening at the baseband, right? So let's say if I look at these 2 samples, and I'm advancing this way, then I have 0, 0, 0, 0, 1, 0, 1, 0. This is your first sample, x of nt. And then the next one is 0, 0, 0, 0, 1, 0, 0, 1. So this is your x of n plus 1 t, right? And then so on. So this is what I'm sending to the line. What happens at this point? Well, this goes into some transmitter and then some receiver on the end. And this is where you modulate, demodulate, do all sorts of things, encode, decode, and so on.
You need the AC and AC,
Yeah.
right?
It can be just sent baseband
Yeah.
through the line, or it can be sent to the satellite and back. You know, and it is really not that relevant from the standpoint of how this process works at the baseband. The PCM part of it is actually going through sampling and quantization and digitalization into binary format. So this is PCM. Okay. Now that the signals are digital, that allows another very important thing, and this is time division multiplex. In telecommunications, very rarely you have resources that are completely dedicated to communication. Most of the time, we have shared resources. You have multiple communications that are sharing same channel, same communications line. And there's always a question of how do you multiplex them? We know several ways of doing them. The one of the most prevalent one is time division multiplexing. And that's the one that we have implemented in telephony, also in
CDMA.
So time division multiplexing, time division multiple access. Multiple access. The one thing that you notice is once you digitize the system, then this is not really continuous, right? You have a bit, and then you can insert something in between here. I should really go back to this figure here. You can see that I have this value, and then I have here that I'm not transmitting anything, or I get rid of this whole portion of the signal. So the principal idea here is I can interlace multiple signals in time and use the same line to send the multiple signals and have them share this particular line. The way how this scheme works is, let's say I have n users, and I'm going to call them U1 through UN. Each one of them has a rate. The rate of the first one is going to be Fs times n. The rate of the second one, R2, is Fs times n. For the sake of simplicity, I'm assuming that all of them have the same rates. This is your telephony. Every single user is generating 64 kilobits per second of the data stream. So you have n of such users. Rn is going to be Fs times n. And I have the shared communication line. Let's say this is an optical fiber that connects, just to give it an example, that connects New York to Paris, right? And I'm multiplexing multiple users here. The way, and then on the other end, I'm doing a process that is reverse of this process that I have in transmission. So this is again R1, R2, Rn. And this is again U1, U2, Un. So you can think of this as a rotating switch, right? So let me kind of put it this way. The switch that rotates this way on the transmission side, and switch that rotates this way on the reception side. So I have the rate R1 here, and let's say the rate on this line is n times Fs times n. Okay? So here's how it works. This switch gives the exclusive use of the line to every pair of the conversation for 1/n of the time. So if you have, this is your time frame, then you take that time frame, divide in n equal time chunks, which we usually call time slots, and this time slot is assigned to each pair of conversations, in a circular fashion. Now this one over, let's say, over a certain interval accumulates Fs times n times the interval number of bits. Well, when the time comes, it needs to send all of these bits that it has accumulated over the same frame. It needs to send them over the portion of the frame. So that means that the rate during that portion needs to be much higher. As a matter of fact, this rate here needs to be n times higher than the rate for each individual user. Right? So to give you an example, this is 64 kilobits per second. And let's just, for a case of example, if I have 10 users here, then what should be the rate on the line? 640 kilobits per second. In a North American hierarchy, in a North American T1 hierarchy, we have that n is equal to 24. So we multiplex 24 users on a single line. Right? So there's 24. This one is called, in North American hierarchy, 64 kilobits per second is referred as DS0. So that's the basic rate that comes from one user. And 24 of these guys form what we call T1 line. So if you look at the rate here, there is a rate on the T1 line. So T1 rate is going to be 24 times 64 kilobits per second. And then we add an auxiliary channel that we use for signaling that is not carrying user data but just used as a signaling for the communication system. This one is 8 kilobits per second. And this gives us of 1.544 megabits per second. And that's the rate that you quote for T1. When we say T1 line, we all know that this is roughly 1.5 megabits per second. And so if you get T1 line delivered to your home, that means you have a 1.5 megabits per second dedicated circuit that you can use for the data transmission. Okay? I'm not going to spend too much time, but this is how we do it in Europe. Does anybody know in US? Do you know how is this structured in Europe? What is E1 line?
That's 2 MBS.
2 megabits per second. So in E1 line, we actually also start from 64 kilobits per second as a basic channel, but then they have 32 channels, each one 64 kilobits per second. So when you multiply that, it ends up 2.048 megabits per second. So it's the same concept. It's just that it's more users. You have 30 users plus 2 signaling channels on the same E1 line. Okay. But and then what happens is then you can kind of build the hierarchy as you go. Now, just like I multiplex multiple DS zeros into single T1 line, I can multiplex many T1 lines into upper level, and then you have DS0, DS1, DS3, DS5. So it goes into ever higher and higher hierarchies. Every time you go, the rate on the line here becomes larger and larger. And this is how you can think of these like rivers that all go into that one large river that goes into an optical fiber that is, let's say, transatlantic or transpacific, and then it gets parsed out at the very end and sent to various directions. Right? So that's how all of our landline data travels. Okay. Now, let me talk about. So these are the examples of some of the things that are enabled by sampling theory. Let's take a look at, now back to our linear system theory. Let's take a look at a dual of time sampling. Which is going to be your spectral sampling. What was the problematic? I hope I have trained you by now. But what was problematic with this equation here? When I say x hat of nt is equal sum when n goes from minus infinity to plus infinity, x of nt or x quantiles of nt delta of t minus nt. There are two things that are problematic. Which are the ones? First one,
We can't do an impulse.
first one is delta, right? That's a good one. What is the second one? Infinity, right? So remember we started from this and then we derived the spectrum of this. And we said, well, the spectrum of this is periodic extension of the baseband spectrum in a frequency domain. And then we addressed your concern, and the concern was, well, what if it's not delta? Well, it turns out this can be any pulse chain, and what happens as a result of that, this spectrum is not constant across the board anymore, but as you move further in frequency, it kind of starts, decreasing as as the Fourier series coefficients, because you're essentially, what you're doing here is you're multiplying your x of t with the Fourier series, right? And then we saw that most Fourier series have coefficients that decrease as the n becomes large. So we addressed that question of delta. If we can sample with square pulses or exponential pulses or whatever is the periodic waveform that I can obtain. But there's still this
Albert infinity?
problem here of infinity. So is there a way for me to determine the spectrum of the signal by looking at the portion of the signal? And of course there is, right? Because we can never look infinity, right? So whatever we put on a spectrum analyzer is always obtained by looking at finite duration of the signal. We just look at the portion of the signal, and we would like to be able to say something about the spectrum of that signal. How do we do that? Well, we do that based on this. And what we're going to do over next, couple of boards here, is talk about essentially determining the spectral content of the signal by looking just a portion of the signal in a time domain. And this is a prelude to something that's called discrete Fourier transform. And I know we love our integrals and they're all elegant, but it's, math is pretty, I should say, nice and round. But what happens is, in practice, whenever we are faced with the problem of determining the spectrum content of the signal, the only practical way of doing that is through a discrete Fourier transform. And the body of knowledge that you have by now helps you understand this mathematically. But what we're going to start doing as of right now is looking at how practically we actually do these things. We do things discrete in time through sampling, and we do that finite in time because we just have not enough life to wait for infinity to come, right? So let's look at now what happens if my x of t that I'm sampling, it does not extend over the entire t-axis, but is localized in time. This may happen two ways. It may be that just signal is local in time, but it may be that the signal lasts for very long, but I just took scissors and I cut a piece of the signal. And the question is, can I say something about spectral content of the signal by looking at just a portion of that signal? So I'm not going to consider a time-limited signal x of t. And it's kind of funny. Remember the two worlds? One is the frequency domain, and the other one is the time domain. So far, I've been living in time domain and looking into frequency domain. So the sentence was, consider a band-limited signal x of f. Now I'm actually in a frequency domain looking over at a time domain and say, consider now the signal that's time limited, right? It does not extend over the entire t-axis, but exists only on a portion of the t-axis. So what that means, x of t is identically equal to 0 whenever t is greater than some tau. Right? So what does my signal look like? My signal look like this, t, and this is my tau, and after that there is no signal. The signal stops, right? So this is x of t. It starts at 0 here because. So let me formulate the spectral sampling theory. First of all, let me define x of omega is the Fourier transform of x of t. Right? I'm going to need that for the definition. So, spectral sampling theory. It says let x of omega be a Fourier transform of x of t. Then x of omega may be reconstructed in a unique way from samples of x of omega taken at discrete frequencies. Take at discrete frequencies delta f smaller than 1 over tau hertz, where tau is the duration of the signal in time domain. So, another way to say this is the whole. Let me go back to that a little bit later. Okay, so let's see, where's my? Okay, so this is more. So let's look at this a little bit from our knowledge of the sampling theorem in a time. So here I have a signal x of t. What does the Fourier transform of this signal look like? It's a continuous function, right? If I have a signal that is like this, it's an energy signal. I do Fourier transform and I get a continuous function in time. So now what I'm saying is, let's say I have, let me just start drawing. So if this is your x of t, so this is my world, this is time versus frequency. So how does my Fourier transform look like? Let's say this is it, x of n. And it's a continuous function of time. So now what I'm saying is, well, I can get back to this function here, x of f, by not knowing all its values. I don't have to know all of its values. All I need to know is some discrete set of values, so I can sample in the frequency domain and not know this entire curve, but know the samples at certain frequencies. Right? This is what I know. Right? You can visualize back your original spectrum, but you don't have what is dashed here. You just have the values at the discrete points. And it says I can reconstruct back my signal by knowing only these discrete points. If I'm sampling in a frequency domain, guess what is happening in a time domain? Periodic extension in a time domain, right?
Yeah.
So here is what I'm actually doing in a time domain. And this is what I'm doing in time domain. Now, when you see this, you can say, duh, right? Because this is what? This is periodic signal. Periodic signal, what does it have?
Discrete.
No, not discrete. What does
energy?
Periodic signal, what's the automatic trigger? Periodic signal, Fourier series. So guess what am I drawing here? I'm drawing Fourier series coefficients, right? So now we've went full circle, right? You actually, if I sample this in time domain, I'm periodically extending in the frequency domain. So if something is discrete in one domain, it's periodically extended in the other. If I take my signal in a time domain, which is finite, and I extend this periodically, then what happens to the spectrum of that signal? It shrinks into its harmonic components. It shrinks into its Fourier transform. And guess what? Those Fourier transform coefficients are going to be samples of the spectrum of the original signal. How cool is all of this, right? So let me go through formal.
That's magnitude x of f?
It is magnitude, but really, there's no way for me to draw complex numbers here. So sometimes I just draw x of f, knowing that even though I'm representing this as a real function, if you kind of probe the value here, it's a complex value that contains magnitude and phase. But that's why I there's no way for me to draw complex. But imagine this is a complex function. Right? Do you follow the explanation, the difference, right? The way how I should draw this is three-dimensional, right? Somehow. Where one dimension is the magnitude and the other one is the phase. And then every one of these samples is also a complex number that carries magnitude and phase of this particular component. So this is your x of NF, NFS, or NF, and delta f, let's say, where delta f is this sampling. And this here is, this is tau, this is x of t minus n tau, and then sum over n. Like periodic extension of this signal in a time domain. So let's prove this so that we kind of see where it's coming from. And this has tons of implications, very interesting ones, right? You have to understand, this will help us understand what is it in the world that we're doing when we are doing discrete Fourier transform. There are stuff on the spectrum analyzer that you're setting. They say averaging time, resolution, sampling rate, all of these things. So bandwidth, all of these things. So this will help us understand what all of these actually mean. So proof. We start by saying x of, there's a typo here, right? No, x of omega is equal to integral when t goes from minus infinity to plus infinity, x of t e to the minus j omega t dt, which in our case becomes an integral when t goes from 0 to tau, x of t e to the minus j omega t dt. Why? Because our signal is time limited. It only exists between 0 and tau. Right? So let us construct a periodic extension of my signal x of t. So this x of t0, where t0 is now a period, is going to be sum over n. So n goes from minus infinity to plus infinity, x of t minus n t0. All I need to know is that this t0 is greater than tau, right? I'm preventing overlap in a time domain. Sounds familiar? I'm trying to separate them in a time domain. Why am I trying to separate them in time domain? So that I have a unique reconstruction of the signal in a frequency domain. Now, what about this signal? It's a periodic signal. So since it's periodic, I know that it has Fourier series, and I can determine the Fourier series coefficient. So x of t0 periodic. Therefore, it has a Fourier series. So xt0 of t can be represented as sum n goes from minus infinity to plus infinity sum dn e to the j n omega 0 t, right? Where this is our exponential Fourier series, and we know how to determine these coefficients. This omega 0 is the fundamental frequency, 2 pi over T0. Okay, so now, how do I determine these dn's? Well, dn's, we know are determined as 1 over T0, integral over T0, x of t, e to the, or I should say x of T0, e to the minus j and omega 0 t dt. But in our case, this becomes 1 over T0, integral from 0 to tau, x of t, e to the minus j and omega 0 t dt. In principle, I can integrate this extended periodic waveform over any period. If I choose to select the period from 0 to whatever is the T0 that I set up, then this periodic function essentially is identical as x of t over this particular period. So and there is no need to integrate beyond tau because my function x of t is 0 after tau. So this is, these two are equivalent here. So now, but if you look at what this is, look at it here. This is a Fourier transform of this signal. If you compare these two, what is this? This is the value of the Fourier transform at what frequency? Frequency omega equal n omega 0. So this is essentially x of n omega 0, which is the sample of the Fourier transform of the original signal. Okay? So now, knowing that, we can see that dn is equal to 1 over T0 times x of n omega 0. And our periodic waveform, x T0, which is sum when n goes from minus infinity of, let me just do this, x of T0 of t in time domain, is sum when n goes from minus infinity to plus infinity, 1 over T0 x of n omega 0, and the samples of the spectrum, e to the j n omega 0 t. So that's how I can represent my periodically extended signal. So now, so let's look at, so this is the periodic extension. I can represent this periodic extension in time domain by looking at the samples of the spectrum of the original signal. So we have two reconstructions. Let's first look at reconstruction in time domain. Okay? What was the reconstruction in the frequency domain when we were doing sampling in the time domain? Let's say I do sampling in the time domain. The spectrum of the signal is periodically extended in the frequency domain. How do I get my signal just looking at the frequency domain?
Low pass.
I have to low pass, in the frequency domain and just get the main lobe, right? So if I have the signal x, this is my xt0 of t, right? How do I get my original signal?
Sync function
Not sync function.
Low pass.
I can't low pass it or box it, right? I need to box this part, right?
multiplied by the
So I have to multiply low pass in a frequency domain meant multiply with the rectangular pulse, right? Here, I'm going to multiply with the rectangular pulse in a time domain. So to reconstruct the signal from its samples of in a frequency domain, I just have to pick one of the periods, because sampling in the frequency domain did the periodic extension in a time domain, so all I need to do is box one of the periods. So the reconstruction in a time domain, I can get my signal x of t by saying, okay, this is going to be xt0 of t, this guy, multiplied by u of t minus u of t minus tau, right? All I'm doing is taking my periodic extension and picking one of the periods, which is a dual of the low-pass filtering that I used to do for the sampling in a time domain. So another elegant way to write this would be xt of t multiplied by pulse, in this case t minus t0 over 2 divided by t0. No, this is not. T minus tau over 2. So I position this pulse at tau over 2, and then I just cut tau of the width. Okay, so that's easy. That's reconstruction in tandem. And that was easy way in the other one too, because once we realized that the sampling in time domain was periodic extension in frequency domain, it was easy to understand what needs to be done. Get rid of these replicas and just keep the baseband. Here, the sampling in the frequency domain is a time periodic extension in time domain, so just pick one of the periods. So this is easy. What does this mean in a frequency domain? What do you guess?
Convolution with
Convolution with a
sync function.
with the sync function, right? So exactly the same thing. So let's just do that. So reconstruction in the frequency domain. In the frequency domain. We say xt0 of omega was sum when n goes from minus infinity to plus infinity, 1 over t0, x of n omega 0, delta omega minus n omega 0. And okay, so this is equal sum when n goes from minus infinity to plus infinity, 1 over t0, x of n omega 0. Let's see, what is it that okay, so this is the spectrum of the signal. Oh, okay, sorry. I see what I'm, sorry about that. So this is a sampling of the frequency, right? The spectrum of this periodically extended signal, x of t0, is going to be discrete. It's going to be all these components, right? And delayed at this point. The spectrum, this is the Fourier transform of this guy, right? Where dn is 1 over tx of n0, and then Fourier transform of this guy here is your delta pulse. So now, if I want to get back to my x of omega, which is the spectrum of the original signal, x of t, if I want to get this one from the samples from its samples, then I have to take the xt 0 of omega, and since I'm multiplying by the rectangular pulse in a time domain, what this means is I need to do with a sinc convolution. I need to do convolution in a frequency domain with the Fourier transform of this guy. Well, the Fourier transform of this guy is going to be essentially tau over 2, not tau, times sinc of omega tau over 2 e to the minus j omega tau over 2. Okay, Where is this coming from? This is a Fourier transform of this pulse. There is a sinc part, which is coming as a Fourier transform of the pulse, and there is this delayed part that is coming as a result that this pulse is delayed in the time domain by tau over 2. So how do I do this convolution? Where this is essentially, if I substitute what this guy is, this is essentially this what I have over here. So this becomes sum when n goes from minus infinity to plus infinity, 1 over T0, x of n omega 0, delta omega minus n omega 0, convolved with tau, tau times sinc omega tau over 2 e to the minus j omega tau over 2. Now, there's nothing easier but convolution with delta pulse. For delta, when you convolve with delta, you get your function back. When you convolve with the delayed delta, you get your function delayed across the axis. The only difficulty that you may have at this point is there's no time here, right? It's all omega, but we don't care. We just do this mathematically. So this would, if you convolve this delta with this sinc, it would just move the sinc to delayed by n omega 0. So you end up here that your x of omega is going to be sum when n goes from minus infinity to plus infinity, tau over T0. Then I have sinc omega minus n omega 0 times tau over 2, and then e to the minus j omega minus n omega 0 tau over 2. And then in this case, I have assumed that my periodic extension is the relationship with tau and T0 is an arbitrary, except that tau 0 needs to be greater, T0 needs to be greater than tau. If I assume if T0 is equal to tau, meaning that I'm doing the periodic extension just like I'm doing it here, then I actually end up with x of omega is sum, n goes from minus infinity to plus infinity. There's something missing here.
The x of n omega.
Yeah, this guy is missing, right? So tau over T0, x of n omega 0. So I get x of n omega 0, sinc of omega minus n omega 0 times tau over 2 e to the minus j omega minus n omega 0 tau over 2. Remember this omega 0 was equal to 2 pi over tau, right? Because tau is equal or, which is 2 pi over t. So that's how often I need to sample them. In other words, my sampling frequency in frequency domain, or the separation of the frequencies that I need to take in a frequency domain is 1 over tau, when the tau is the length of the signal in a time domain. So, if you look at this, this is very much similar to our reconstruction formula that we originally looked in the case of a time domain sampling. Here are the samples. Of the spectrum. And this is my weighting function. This is the reconstruction function. Okay. Okay, so I'm going to stop here. Let me give you some problems. So here are the list of problems, 8-2, 1, or it should be 8.1, 2, 3, 4, 5, 8, 13, and then 8-3-1, -2, 8-4-1, and 8-5-1. So those are all relevant problems. I have 2 minutes, so let me go through that. There was a question before the class. Let me address that one. I don't think I'll have enough time to solve it, but let me get you started. Because there's one thing that, this is the problem that was on the test. And, you know, if you overlook one simple thing at the very beginning, then it gets pretty difficult. So let me address this one. So it says find the zero state response, y of n. So of the linear time invariant system when x of n is equal to 3 n minus 1 u of n plus 2, and your h of n is given as 1/2 delta of n minus 2 minus 2 to the n plus 1 times u of n minus 3. So that's you have an input and an impulse response, and we know what the output is. Y of n is equal to x of n convolved with h of n. Right, this is our output. And you can do that directly, but before you actually do that, what was required in this problem is to look at a little bit closer this h of n. And in particular, I could rewrite this h of n as 1/2 delta of n minus 2 times u of n minus 3. And then I can say minus 2 to the n u of n minus 3. Right, because this 1/2 and n plus 1 would cancel. This is not going to work, plus, right? Plus. So now, you look at this part here, and what is this? It's a product. Let's just draw these two functions. This is n. Where is this delta? 1, 2, 3, 4. Here's delta. This is delta of n minus 2. Where is this guy starting? Here. So what's the product of these two? So the product is 0. So this whole thing goes away. Right? And what you need to essentially do is y of n, which is a convolution 3 n minus 1 u of n plus 2 convolved with minus 2 to the n u of n minus 3. And I'm sure you can handle this one, right? This one is a table, right? So that was a trick. You know, I don't know if, you know, it is one of those things, you know. If you did the homework, you know, you would know about this trick, right? So you just know it for the exam.
I went blind.
Huh?
I went blind in the exam.
Yeah.
He was.
I got cocked.
Okay. So that's it. Have a great holiday, and we'll pick up when you come back. We just have 3 more classes, right?
Two classes that we're doing because.
2 classes of
Yeah,
the
one is not enough.
Classes are really classes.
So what I'll do is let me figure this one out. Let me see if I can finish what I did next class. Get this back to class. See this.